We have Tynes from University of Chicago. He is in computer science. His advisor is Ian Foster, and his practicum has been at Los Alamos National Laboratory.
I've got a clicker for you.
All right. Hi, everybody. I'm Mike Tynes. I'm a fourth-year CSGF fellow and a fourth-year PhD student in the computer science department at the University of Chicago. Today, I'm going to be talking about a few research projects that I've been working on that the CSGF has supported. These explore a few directions in machine learning force fields for molecular dynamics. And this is work that I've done both at the University of Chicago and in my second practicum at Los Alamos National Laboratory. All right, so real quick, molecular dynamics is a computational technique that allows us to understand materials and molecules at the atomic scale. It has wide applications across fields like medicine, manufacturing, materials engineering. We can use it to characterize and design new plastics, new materials for natural gas capture, to understand how fusion reactors, the materials in them degrade over time, and many other applications. So in molecular dynamics, at every time step, we need to evaluate the forces acting on every atom. And this is the computationally limiting step. Computing these forces is very expensive, and the method we choose to compute these forces dictates both how accurate and how expensive our MD simulations are going to be. So I'm just going to give an overview of some of these methods. Right, the gold standard are quantum mechanical methods, which model the interacting electrons around every atom. This best reflects the physics of how atoms really interact, but it's also the most expensive way to do this. And it limits MD simulations to roughly tens to hundreds of atoms and the picosecond timescale. So we could ignore the electrons and instead model the atoms as classically interacting particles. We'll lose a lot of that accuracy, but we will also gain quite a bit of efficiency, and it'll unlock scales of, say, tens of millions of atoms in the microsecond timescale. We could further remove degrees of freedom and group atoms together into beads and model the interactions between those groups of atoms. And now we can model tens of billions of beads. So depending on how big your beads are, you may unlock another order of magnitude or so in number of atoms. And also because the beads, their dynamics are smoother, we can take bigger time steps and unlock a few orders of magnitude of time scales as well. So this was the spectrum of methods available for computing forces in molecular dynamics. But more recently, machine learning has kind of changed the game. So we can fit machine learning models to forces from quantum mechanics and get a model that is nearly as accurate as those quantum mechanics, but nearly as fast as the classical force field. So we can now simulate, let's say, millions of molecules or millions of atoms at nearly quantum accuracy and unlock nanosecond timescales at this accuracy. So this is something that wasn't possible before, and it's great, but these machine learning models are only as accurate as the training data they have, and there may be gaps in these training sets. So this is a problem that I address in part one of my talk, where we talk about on-the-fly learning for these force fields. So briefly, on-the-fly learning is a paradigm in which we assume our model can never be fully trusted. So we're running a molecular dynamics simulation, and at every step, we're evaluating one of these machine learning force fields, and we check whether the uncertainty is within some threshold or not. And if the uncertainty is below the threshold, that's great. We trust the model, and we move on to the next time step. And if we don't, we actually run the quantum mechanics and update the machine learning force field, and then we move on. And this has several advantages. We can detect errors due to gaps in our training sets, which might occur around rare events that we didn't sample when we built the initial model. And we can do this with only collecting the data we really need for the simulation at hand. But there are several disadvantages. Right? It's not always so clear how to choose this uncertainty threshold, and it may not even have a clear physical meaning. Updating the model parameters during the run of the simulation can also disrupt the sensitive dynamics that we're trying to model. And also, I've outlined a serial paradigm for doing this on-the-fly learning, but you may notice that we're running quantum mechanics, we're updating a force field by training a machine learning model. These are very different computational tasks with different resource profiles. They should really be done on different hardware. So what I've outlined here ignores that. So I'm going to address all of these issues, and we're going to start by automatically choosing the uncertainty threshold with a tool called Proxima, which was developed in my group. So rather than choosing this uncertainty threshold up front, we asked the scientists to specify an error tolerance. So I'm willing to let the machine learning model be this wrong. And then when we update the model, we can actually observe how wrong we were and use this control equation to adjust the threshold to be more conservative when we're making big errors and less conservative when the errors are small. So this worked well in a Monte Carlo setting. So this is a Monte Carlo simulation of methane at various temperatures. This experiment compared a static threshold that was chosen up front to this dynamic threshold with Proxima. And as we increase temperatures, we're increasing the variability in the states we encounter, and we increase the error that we see in these simulations. But Proxima is able to catch this and make the uncertainty threshold more conservative and decrease the errors in these simulations and keep us within this error tolerance here. So that was a strong result, and this was in a Monte Carlo simulation where states are chosen by randomly perturbing the system and accepting them if they have a low enough energy. But when I tried to use this for molecular dynamics, it didn't work. So in molecular dynamics, we're smoothly evolving the positions of atoms over time. And when we're abruptly switching between using the machine learning force field or using the quantum mechanics, we're violating the smoothness assumption in the numerical integrator for molecular dynamics, and we're introducing unphysical behavior. So if we look at the oscillation of the volume of my simulation cell over time, the black dashed line is the quantum mechanical reference. And using Proxima, so we're turning the machine learning model on and off in these shaded regions. And when we start doing that, we introduce these high frequency modes and this volume oscillation. Also, the oscillation is amplifying over time. So we've disrupted the dynamics. And we think that has to do with introducing these discontinuities or non-smoothness in the potential energy surface that's generating these forces. So to fix this, I introduced a smooth blending parameter. Right? So rather than abruptly switching between the machine learning force field and the quantum mechanics, we take this parameter lambda that's between 0 and 1. We start at 0, which means we don't trust the machine learning. As we encounter states that the machine learning uncertainty is low, we slowly bring lambda up to 1 and mix in machine learning forces and mix out the quantum mechanics. Once lambda is 1, we don't run the quantum mechanics and we get our full machine learning speed up. If we encounter a state we don't trust the machine learning model, we slowly blend the quantum mechanics more in. And we can see this working. All right, so on the bottom we have lambda changing slowly over time, and in the top in the red line we can see that we're tracking much more closely to the quantum mechanical reference. We don't see these high frequency volume oscillations, and this amplification is much smaller. So this is something we're happy with, but we're really just looking at 1 degree of freedom in the simulation, right? Just the volume. When we run molecular dynamics, we're often interested in more complicated structural and dynamical properties. So we're going to look at one of those called vacancy diffusion. So we have a lattice with 1 atom removed, and over time the atoms near this vacancy are going to hop into this vacancy. This is an important property of materials, right? It determines a lot of structural mechanical properties of materials, and it's a complicated dynamical property. So if we can get this right, we're confident that we're doing dynamics right. And so we can see we've just measured how often these hops are happening over time, and just running the quantum mechanics. This is what it looks like, and we've introduced an 80% error doing the naive Proxima, but introducing the blending, now we're back down to 5% error, which is within our error bars. It's pretty close. And so this is a result we're very happy with. This smooth blending has corrected our ability to model the sensitive dynamics that give rise to vacancy diffusion. So that's wonderful. What I was a little less happy with was how long this took. So this brings us back to the resource heterogeneity that we talked about before. Right? We're running quantum mechanics and updating machine learning models on the same node. Because we're doing a lot of quantum mechanics, I chose a CPU node, which means that the machine learning updates are very slow. We are using a neural network for this, so despite accounting for only 1% or less than 1% of our step count. You can't even see it on the graph here, right? It accounts for 45% of our runtime. So that points to a better architecture for doing this, a more HPC-oriented architecture. So this is something I'm working on now, calling it Cascade, and it's basically just a distributed implementation of what I've already outlined. So we've broken up all of the different tasks into different agents that act asynchronously. Oops, I don't want to do that. Right, so we have dynamics runner agents, a machine learning force field trainer agent, quantum mechanic labeler agent. And these I've built in the Academy framework, which is a agentic asynchronous programming framework developed by my group. And what's nice is you can just write this like a normal object-oriented program, but these agents can talk to one another over networks. They can use backends like Globus or Redis to pass data around, and we can do this distributed across one cluster or many clusters, depending on what we're doing for the machine learning, what we're doing for the quantum mechanics. We can make good use of the HPC resources available to us. So this is something that I'm actively benchmarking, and I'm very excited, and I hope that I'm going to be able to build machine learning models that are more accurate in much less time. So I'm going to switch gears a little bit now and talk about coarse graining, which we heard about a different kind of coarse graining in our first talk, so I really love the synergies here. This is coarse graining for molecular dynamics and doing machine learning for that. And so a little bit of background on coarse graining and molecular dynamics, right? We have to group atoms together into so-called beads. Here we're just grouping molecules together into their centers of masses and modeling the movement of these centers of masses over time. And we have to combine the forces somehow. So we just add up all of the forces on the atoms, and that's the net force on the bead. And we use that force field. We build a force field that just models this and use that to model the movements of these centers of mass over time. That allows us to reduce the number of particles we're modeling. But coarse graining has a non-uniqueness problem. So for every bead configuration, there are infinitely many possible all-atom configurations. What does that mean for our force field? Well, a principal way to handle that is to build a bead force field that is an average over all of the coarsened forces of all of the possible all-atom configurations. So there are ways to do this, but a lot of machine learning models that are built for this do not explicitly train to average forces. And that's something that we wanted to do, and we wanted to do efficiently. So we start with a set of bead configurations generated from an all-atom trajectory. And we constrain the bead positions, but we allow the atom positions within those beads to vary. And we do that by separating the coarse and fine degrees of freedom with linear coarsening operators, separating out just the fine degrees and doing equations of motion for those, evolving those over time. Right, and we create many replicas of each system and use that to fill one or many GPUs and just run those until these average forces here, oops, okay, I've got my buttons confused. Until the average forces converge, build a data set of force averages. So right now we have average forces that we've collected by running many replicates in parallel. And we can train a machine learning model to that. Does it do better? Right, so here we're training to the instantaneous forces, just one trajectory that we've coarsened. And here is our average of many parallel replicates. And we've increased the R-squared on held out average forces, that's important, from around 0.1 to 0.3. People that do a lot of machine learning may say, hey, a test R-squared of 0.3 is actually not very big. But you got to remember the signal does have a lot of noise in it here. So these average forces still represent phenomena that are smaller than what this model can see, right? And we've averaged out a lot of information. And actually, in a previous paper from my practicum advisor, they use a model with an test R-squared of around 0.1 to model this structural distribution of particles over space, a radial distribution function. And it's closer to the all-atom than a reference open source coarse graining force field. So even with an R-squared of 0.1, we can do quite well. So I'm very hopeful with this result that I actually just got pretty recently. Improving the R-squared by this much is going to lead to downstream increased capabilities to model these complicated structural and dynamical properties more accurately. So that is pretty much everything. We've talked about using parallel sampling to build force averages, to build better training sets for coarse graining models. Right? We've talked about on-the-fly learning, which really the high-level goal of my work here is to build systems that can automatically choose between quantum mechanical methods or simulation tools in general, and automatically tune machine learning models to meet accuracy or budget constraints and make better use of high-performance computing. So with that, I'd like to thank my advisors and thank the CSGF, and thank you very much for listening.